I don't know how. We double check. Now it's working? Okay, thanks. I don't know what happened. So I'm not going to be talking about some big fancy models. Instead, I think what I'm hoping to show you is a story of a real world application where a very mature field has a set of analysis tools that have been around for potentially decades in some cases, but where machine learning can step in and fill voids and gaps in capabilities. But to get started, let's see, does this work? Okay, to get started, who am I and why am I here? So this is just a brief overview of my background. I got my undergrad degree in chemical physics at Rice University. I graduated in 2009, I think. Yeah, and then after living abroad doing particle physics research in Argentina, I went to UW-Madison and did my PhD research on this experiment called HAWK in Mexico. You'll see in the photos of myself that mountains can play a key role in my professional and personal life. But we were doing cosmic ray and gamma ray physics studies on this mountaintop in Mexico. And this will also be a theme. So, I published some work. That was my PhD research. I did touch hardware. I wasn't just a data scientist and analyst. But importantly, I made that work useful, and I released my code that I developed as part of my PhD for the open source community. And I encourage you all to do the same as you go through your academic and professional careers. So after my academic time doing particle astrophysics research, I actually joined this venture capital firm called InQtel. They do investments for the intelligence community. And it was during that time that I got to apply the learnings that I had, the skill set that I learned being an astrophysicist in more real world applications, especially those concerning the intelligence community. So I built dashboards that displayed really important information regarding deepfakes, because at the time, the state of the art in generative machine learning modeling was things like GANs, and then to some extent diffusion models at that point. That was on the order of like 6-7 years ago. Did some statistical studies with them as well, but that led me to that experience led me to being a staff scientist at Los Alamos National Laboratory, where we solely focus on problems of national security. In my role as a scientist, I work on a number of problems, technical problems, including those in remote sensing, doing change detection, and the things that I'll be discussing today as well. But I also have a fellowship in science policy as it's applied to the Americas. Happy to chat with folks if that's of any interest. Also, just a brief, who am I? Again, I mentioned mountains are important to me. Here's me with one of my daughters strapped. I didn't take her up to the very top, but I definitely go skiing with them. I have 2 of them now, and I do things like play piano and make burritos with my children and cats. What brings me here? I have a formal collaboration with Professor Peoples, so I'm very lucky to call him a collaborator. And we work on things related to computer vision and remote sensing. In particular, I'm not going to steal any of his thunder, but we are working actively on this spectral convolution layer. And I'm not going to present anything on that because he and his team have submitted this. But what's allowed us to do that collaboration is our formal collaboration with the TAMU Lanel office. He has a seedling proposal that got funded and is working on, and we hope to continue that. And I've also guest lectured for him around this time last year as well. So thank you again, Josh. I really appreciate that. So here, I'll now get started on the actual technical stuff for the talk. I'm going to do a brief intro, and then we'll go into some of the problems associated with the machine learning components of this. So what is hyperspectral imaging in the context of remote sensing? So what hyperspectral imaging is an extension of just natural normal cameras, except instead of just RGB or 3 channels or 1 channel, instead you have many channels associated with your sensor that are very finely binned in wavelength. And so you can have a number of different types of sensors that could be on a satellite, something that's airborne, or something that you just put on a tripod and make observations. What I'm showing here is a diagram of one of these sensors that's mounted underneath an airplane, and you fly it over the ground. And with those capabilities, you're able to capture very finely detailed information about about the scene that you're looking at in very fine details in spectral and spatial wavelength. In particular, I'll be talking about a very specific region of the electromagnetic spectrum where the atmosphere is fairly transparent to light. And in particular, it's this long wave infrared. And it turns out that that makes things easy to mount under a plane, one of these sensors, and do studies with it. So if you focus in on this transparent region of the electromagnetic spectrum, we call it the long wave, or LWIR, you can do things that are really interesting with this type of data. You can collect this imagery, which has lots and lots of spectral channels, and it allows you to do things like material identification. Because you have so much information, in the spectral domain, you're able to say with pretty high confidence, I have something that I'm interested in from my spectral library, some substance of interest. And then you can use some kind of classification model and say with very high confidence, hey, I think I see that material. So you can do this for a number of different applications, for land use, forestry, this kind of thing, agriculture, number of use cases. So very briefly, the goal of using this type of methodology is to remotely detect and identify materials of interest. Those could be gases or solids. And there's some physics involved in this. Indeed, when you look at, this is just an image of, say, some kind of solid target that you might be looking for, some kind of solid material. It's a little bit different from gases, but it's very similar. Basically, you have modeled your target with a black body radiation at some temperature. The natural emissivity, the thing that identifies that material, it's unique to that material, gets convoluted and convolved with various components of light from the atmosphere. That could be light that's coming down from the atmosphere, and then you have to transmit through the atmosphere, so that's this transmission. And there's also just light arriving at your sensor that's convolving the signal that you're looking for. Again, this is the unique identifier of that material, getting convolved with all these different things. And what you actually measure at your sensor is this L value, radiance, basically the amount of energy in a specific wavelength band arriving at your sensor. And so the goal is, can we take this information and back out all of these things, but most importantly, what this material is? We have a number of efforts at LANL that are related to this type of work. We have some projects, these are funded by government agencies for this kind of work. The Awesome project, not my naming convention, looks at the grain size of those solid materials and understands how does that spectrum change as a function of different material properties. The double take experiment or project looks at the time domain, so looking at a target over time and understanding how things change and what kind of information you extract from that data collect. And then the machine learning focused projects that I'm involved in or have been involved in are this Living Backgrounds project doing 3D reconstruction and 3D scene understanding with hyperspectral imagery, and the Paradox project, which is primarily involved in getting physics-informed machine learning and extracting information from our data. These two projects have actually been wrapped up into a larger venture project called Focus, but that's just a LANL internal kind of thing. So briefly, before I get on to some more details, I just want to mention the way I think about machine learning when I'm doing my work on a day-to-day basis. Most people, when they talk about ML, they're really talking about the algorithms. What's the fanciest new LLM or something? And I'm not going to be showing that today, because the data that I'm showing is the problem that I'm showing is more interested in the type of data, the quality of that data, and what you can do and what kind of questions you can ask of that data. That's a big determining factor in the type of algorithms you should be applying. You really don't want to be memorizing your data, but what kind of algorithms can I throw at that type of data? And then less important for this use case is the hardware. Of course, NVIDIA takes care of that for us for the most part. But in some problem instances, you need to think very carefully about, do I have enough compute to ask these analysis questions associated with my data and the types of algorithms I'm going to be using, do I have enough hardware to do this in a time scale that might be on the order of, the life cycle of a grad student or something? Okay, so now I'm going to move on to the actual remote sensing problems. And feel free to ask questions, by the way, if anything's confusing or I'm not being clear. The first task I'll be discussing is a hyperspectral target identification. So what does that data actually look like? Well, I just mentioned in one of the previous slides that the type and quality of data determine the type of questions you can ask. So in the simplest remote sensing type of data, you have something like grayscale, where at all of your physical spatial pixels, you only have a single integer value associated with intensity. So you're pretty limited in the type of analysis questions you might want to ask or might be able to ask. But maybe you can start to see the differences between the road and the vegetation, for example. Moving up to RGB, something you might be able to buy off the shelf, some kind of camera, and put on a drone, for example. You now have a vector of 3 values that you have accessible to you. Now you can do a little bit more, maybe start differentiating between the types of vegetation that you have in the imagery. And then finally, as I've already kind of mentioned, the detail associated with hyperspectral imagery isn't just these pixel values, it's and three vector. You have potentially 100 channels where each of these is actually a floating point value, where you have very finely detailed information in spectral and spatial space, where you can go and pull out, hey, here's 1 pixel. What is now you can start to answer really interesting questions. So how do we start exploiting that data? Well, the first step is actually just looking at the remote sensing imagery you have and saying, hey, do I have some kind of signal that stands outside of the background that I should be interested in looking at? And then once you have these regions of interest, these groups of pixels picked out from your imagery, then you can go and say, hey, I'm going to now ask the question, can I determine what kind of material is in that group of pixels or a single pixel? I'm going to focus, because the machine learning problem is a little bit simpler and I have real data, on the target identification piece first. It also is part of the story of me joining LANL. It was the first problem that I worked on. It's a little bit more accessible to start with, and then I'll get onto the detection afterwards. So going back, our goal is, we want to take this measurement that we have up in the sky or up in space, so this L, this radiance value, energy at a sensor, and we want to ask, can we build some deep learning system that's able to do the classification of the materials that are on the ground? Remember, the only information that's really relevant to making that classification is this emissivity value, this epsilon. So a lot of this stuff is just confusers and convolving that information. So can we even build a system that does this, that teases some of that out? But there's one other problem, is that there's not enough real data, real hyperspectral imaging data that's labeled that we can use to train our models. Like, you don't have millions of images with millions of substances that you've planted and you know are there. So the solution comes from this funded project that just wrapped up this last year that I was a part of, called Paradox. And the idea is, well, we actually have plenty of labeled data in the lab. We also have plenty of observed variables out in the wild. Let's combine those, and that's the way we're going to build our data set, which we're going to train our models. So to build our training data, we take our set of library data. So on the gases side, you have information regarding how much gas absorbs as a function of wavelength, and here how much light is reflected by a solid as a function of wavelength, but you use these similarly to build our data set. So we have lots of examples from measurements that are made in the laboratory, so we know those very well. Then you also have real world collects with maybe a few detects, but we don't care about that. What we're caring about is all these atmospheric variables that we can estimate and build up, we can use to our advantage to build up those variables and then convolve those two to build a data set that we know we trust. We know where this data is coming from. It's real, it's collected, both in the lab and out in the wild. So this is how we're going to build our data set, and that's what we did. That brings us to actually being able to train neural network models or building them first. But there's one confounding factor. The first step is that I mentioned at the very beginning of the talk that the remote sensing community is a very robust, mature field, right? This has been around for decades. So it turns out that typically what happens is there's a lot of pre-processing things called whiteners, basically that these classical algorithms that take care of all of this stuff to give us spectra that we can actually work with. Basically, there's a lot of subject matter expertise that goes into this before we can try to build our neural network models. So when I stepped into LANL, that's the type of modeling that was going on. We have a set of training data that we build up from those libraries and the observed spectra and information that I showed you before. We use that physics model, that radiance model that I showed before for gases and solids. We use that physics model to generate simulated, but from real data examples. I should say synthetic, basically. And then we use those SME, the subject matter expert methods to build out what are called white and radiance, something that is kind of normalized with subject matter expertise. So that's something that we can throw into a machine learning model. And indeed, the first model that I played with and tried to optimize a little bit was this 4-layer model. It has these squeeze excite modules, which is kind of a proto attention from back in 2015 or so, before other heftier models came about and more performant models. But we train this just we would as a normal classifier. We know our truth. We know exactly what we're putting into our training data. And so we ask the model to do predictions, and then we update our model weights in a way that makes it more performant. So we can build this. We do it with thousands of materials. So we can get this thing to work. My first contribution as a scientist at LANL was actually taking that very bulky model that took a long time to train, was not very performant in inference, but did okay. It wasn't super generalizable, but I asked a different question. I said, hey, can we take this whitened data that's nice and normalized and then just do a different transformation on it so that we can use different machine learning tools? So what I asked was, can we take this whitened radiance, use an FFT and build up a 2D spectrogram, pretend like this is take this as a 2-channel image, and suddenly we have access to computer vision type models, CNNs. And as a result, I was able to make that model basically significantly smaller and train a lot faster. In fact, I was able to make it a third of the size. I made it train about 6 times faster, and inference was about 3 times faster as well. That training accuracy didn't really change much. That's not super significant, but what was its ability to generalize to the test data set. And that's what you see here too. You see this accuracy curve for that 1D net, the first one that was very bulky. It did fine on the training set, right? It's doing well here in training accuracy, but you see very strong spikes in the test data. So it's not generalizing well. And it just turns out that by restructuring our data, the way we look at it, using our CNN, we both get an improvement in that test accuracy, but also improved generalization. So just access to your data, the way you're looking at it, can be very important. And then I go back to those 3 buckets, but of course I'm leaving out the hardware one. But we know our data, we trust it very well. But okay, this thing is performant, but then how do we know that we know that this model is doing making decisions in a way we would trust? So how do we build more trust into those into our models? You've already seen from those diagrams that the most amount of variation in what's measured at the sensor is coming from those atmospheric effects. The material emissivity doesn't change, that's the same. But differences in collection geometries or atmospheric conditions make a huge difference in what the sensor actually sees. So how do we know that this neural network is actually using those emissivity features and not spurious, non-material specific variables? So one approach to this is taking this existing model that uses this whitening, the thing that tries to take care of all of that stuff from the classical perspective, and then asking instead, can we build a model that instead avoids doing these classical algorithms and just treats the radiance that comes in at the sensor and doing the classification? Can you learn the physics of what's going on, but with a single machine learning model, avoiding all this pre-processing stuff? Now, the way we're going to test this idea out is by first having basically a black box neural network, something that takes that radiance at the sensor, that measurement, and then providing the material class. So can the neural network learn all that stuff? And then the more sophisticated one approach is to build out a set of neural networks that takes care of all of those confounding variables, but also allows us to make that classification on something, on the emissivity, the thing that we care about for material identification. So this is our first approach. The idea behind this is you can separate all these variables out from our, at least in this case, the solids equation. These are our physics modules. Can those learn those physically meaning variables that we can also use as contextual information about the measurement we're trying to make? You still need that subject matter expert to look at these things, but at least you have this contextual information to give you a sense of whether that model is performing this material classification might be correct, but are these other things looking within nominal values as well? So we did that, and here are a couple test examples, some test data. The green is the original injected signal for all these different variables. The physics neural network is providing an output as a function of wavelength that you see here as well. And then the red just shows the residual. So you see that we can train these modules to, this larger neural network and modules to do pretty well. These are fairly well matched. So it seems like a pretty solid success. Although you start to see some potential degeneracy. The thing we care about, again, is this emissivity. You see here the neural network kind of gets it off by kind of the standard amount, but if you look carefully at the temperature, that's adjusted too. So that tells us that this deconvolution that we're asking the neural network to take care of is actually maybe a little bit, there's some degeneracy in its ability to make these predictions. So while these extraneous variables look fine, there might be some issue in approaching this if you're not careful. But at least we know this type of method will work. Okay, this is still not fully satisfying. We do have output variables that it's learning, that we've injected, et cetera. But we're still not sure, are we using the correct features to make decisions? Is the neural network making decisions that we can trust, not just be performant? The classical example bringing this question up is this paper from 2016 asking, hey, if you try and classify huskies versus wolves, yeah, it does a good job. This classifier did a good job, but the reason it was picking out the huskies is it was because it was finding the snow. Well, huskies, most of those photos are, there's snow in the background, but it doesn't care what the dog actually looks like. It was just like, hey, there's lots of snow, probably the husky. So we want to ask, are we using features that are physically relevant for making our classification? One approach that I'll discuss here is this integrated gradients feature attribution method. The idea here is that the neural networks don't actually need the full scaled image. There's a lot of information. Well, in this case, it's an image data. The neural networks don't need the full scale information of the data that you're inputting. In fact, if you plot the model score, the model output as a function of just scaling basically zeroing out the image all the way up to where you have the full data, it actually turns out that maximum model score can be reached well before you reach the fully scaled data point. So there's information that you can tease out of that. In particular, you can ask where is most of the power coming from in your classifier from this feature. So here I have an example of scaling this input, benzyl alcohol. This is what the white and radiance actually looks like in gray, and I'm scaling it as a function of gradient step here. And you see the decision making is picking up most important features in these dips here, in these curves. So we can use this and compare to what an SME might use for his or her own identification with our radiance values. So here, this is something coming at the sensor for both of these. But here I'm comparing that baseline neural network. That's just a single module. You see it's picking up this very strong feature. Again, not whitened radiance. This is just the radiance at the sensor. It's picking up this strong feature as part of its classification, why it's making that decision. This big modular neural network is also picking out that feature, but importantly, we have the contextual information from those other variables, but also we can tease out that emissivity and say, oh, it actually co-occurs with this feature in the emissivity curve. for making decisions. So that seems like a pretty solid contextual information that we can use for trusting our models. So while these two types of models, the single one and the modular one, end up having very similar performance on our test data, at the very least, this one is spitting out this contextual information. And so I put the checkbox here on our trust box. Okay, so that brings us to the initial step of target detection. Now that we've gone through this kind of simple classification problem in a real world setting. But again, to get to that point, we need to first ask, hey, are there any pixels in my scene which I should be concerned about that are standing out over the background? The way we do this is something adapted from the radar literature. It's called the ACE detector, adaptive coherence estimation. But basically what you do is you take your data image, your hyperspectral data cube, and you build up a covariance matrix, and you have a sense of the mean values as a function of wavelength for your spectral bins. And you build up like a Mahalanobis distance, just like a normalized PCA distance, and ask, hey, do I have any of my spectral library signals? Are they peaking out above some threshold? And I'm going to call that a detection score. Again, not identification. You're just asking what pixels in my scene are standing out above the larger number of background pixels. So you use this method. It's fairly standard and straightforward, but I wanted to make sure I covered it here. So what does this look like? In single image analysis, you might have a hyperspectral. This is a false color image of this simulated scene. So you pass that, you use that to build up your statistics. You get some ACE score, and then you threshold it and say, hey, those are my region of interest pixels. That's what I'm going to take to do my identification. But where this project, the Living Backgrounds project, takes us is beyond this single image analysis and asks, hey, can we harness multiple images from different perspectives to improve this type of detection? And that brings us to using 3D scene understanding methods from the machine learning literature. There is motivation behind using this technique, or at least wanting to think about this technique. Here's some flight paths. Remember in some of those first few slides, I showed you the airplane with the sensor mounted under it. They don't just go over once. They actually fly over and have paths that look like this. I think this is over Bakersfield. Oh yeah, Bakersfield. So they're looking at very specific areas in Bakersfield, probably looking for methane leaks or something. But they have these flight paths. The data collect frequently overlaps as you do this type of flight path, what are called wisps. And so here's another one over the Salton Sea near Los Angeles, or closer to Los Angeles. So these flight paths end up providing data that has overlapping regions. And if we extend that beyond just the airborne detectors, we have capabilities of being able to fly drones. You know, that's very flexible. Maybe not the most precise cameras that we can put on there, but we can certainly do do multiple look collects on the same area, all the way up to capabilities that involve space-based systems, which we can task to look at areas multiple times as it passes over. So there's a lot of motivation for testing out this kind of method. So how would we harness multi-look perspectives on any imagery, but in particular, hyperspectral imagery data? So this brings us to the neural radiance field models. They've been around for, I'm going to say, around 5 years or 4 years now. They were the state of the art until Gaussian splatting came around, but are still very useful in certain contexts. So we took the neural radiance field because at the time that was the only model available. So that's what I'll be discussing here. The idea behind these models is that you take a bunch of images from different perspectives of a scene, feed them, kind of apply them, you know what the geometry of where those images were taken, train a machine learning model to produce novel perspectives that were not part of the training data. So basically interpolate at these kind of grayscaled out perspectives of where the cameras are. So new novel perspectives based on training data that you provided. Can we push the limits of that? the way that this model works is basically you feed in to what ends up being a relatively small neural network. The secret sauce of these neural networks is actually the implicit encoding of this information, but that's just a matter of how you encode the data. But you encode position of your cameras, X, Y, Z, and then their angles, theta and phi, and you ask, output me the color or radiance value of that pixel as I would expect from that perspective. You train it under supervised loss, pretty standard, but it tends to work pretty well for RGB. Could we do the same thing for, can we do the same type of analysis, but using our potential 100 channels? And it turns out that yes, and I don't know why there we go. Turns out, yes, spoiler alert, so we can get NeRFs to learn on really, really large image data cubes from our hyperspectral imagery. What I'm showing here is this false color scene and then an ACE detection version looking at that. So can we use this for our target detection? Can it be valuable for that task? So let's see how we got up to building it. Now, here's where, for now, there's also a data paucity problem. You don't have hundreds or thousands of images of facilities when they happen to have targets in them, et cetera. So instead, what we used was this Rochester Institute of Technology simulation package called DeerSig that is freely available, but you have to first take their training course before they give you the executables. It's basically just a very fancy physics engine doing Monte Carlo ray tracing, but it's very high fidelity. They use it for many high stakes applications. But again, it's just a physics engine. We modeled our simulated data after this Mako sensor that I've actually shown data from that before. I just didn't tell you what we were looking at. Turns out that in this long wave infrared region, basically 8 to 14 microns, they bin those channels, they bin that information to 128 very fine binned spectral channels. So we modeled this since we have real data on it for our other task. We produced a hemisphere of basically 230 different perspectives just to get a sense of what this would look like. And then we injected a very strong signal, plume gaseous signal from sulfur hexafluoride that we can easily see and detect in certain channels, but not in others. So let's take a look at the our first attempt at using NeRF. This is not hyperspectral imagery. I just used single channels. So here's a NeRF model comparing ground truth to the NeRF model output at a channel where there is not very much signal. It's a very weak signal. And comparing to where there is a very strong signal. Of course, you can see that here in the ground truth. The rows indicate the amount of training data that I was using to train the NeRF model, just to get a sense of what my limitations were from our 230 images. And then over here, I have the error metrics, just mean squared error, MSE, as a function of training time, but for those 20, 50, and 80% data. So here, where the signal is weak, well, just by qualitatively looking at the difference between ground truth and NeRF output, it seems like there's not significant differences, maybe in the background information, but otherwise the stack seems represented fine. But where the signal is very strong, you see that at the lowest amount of training data, the plume is absolutely absent. It's not strong enough for the NeRF and not enough data for the NeRF to actually pick up that information. So that's a concern. When we get to 50%, we see it starting to get represented, but it's not fully connected to the plume stack, the smokestack. Whereas when we get to somewhere around like 150 images used for training, well, it's doing a much better job here. At least that's qualitatively what's going on. For the plume being absent or being very weak, we see that indicated by high error at the low amount of data and getting better at representing when you have a lot more data. So that's pretty intuitive. However, what wasn't intuitive, or at least at first, was the fact that for the bin where the plume is very strong, we have 20% having the least amount of error and the 80% having the most. It turns out that what's happening is the background pixels dominate. And so it's actually picking up and trying really hard to represent the plume while ignoring the rest of the image. So you get a lot of error in estimating what's behind it while trying to focus in on that plume. And that's why this error looks so high with more data. It's because it's trying to focus more on this signal that it didn't have before. So that can have high consequences for the type of analysis you're trying to run. So I'm skipping a few steps here, but eventually we were able to scale up to our full 128 hyperspectral channels. So throwing in a whole large data cube. What I'm showing here is a slightly different orientation is the ground truth and the NeRF output when looking at the same perspectives in the training data. And so you see in this false color imagery, yeah, the plume is fairly well represented. Looks kind of nice. We think we're doing pretty well. But then when you go and look at the test data, here's the ground truth, should look like this. There are hallucinations all over the place. There's no plume, it's absent. So clearly this model has just memorized the training data and is not generalizing at all. It's doing quite a poor job and hallucinating all over the place. So this aliasing is common in these types of models, especially when you're just using these models in a naive approach. So certainly at this stage, not trusting our algorithms. Since that initial scaling up to the full hyperspectral imagery cube, we've made significant improvements to the architecture and to the losses we're using. I'm not going to go into major detail here, but one of the main improvements was going from the vanilla NeRF, which I used before, to this MIP NeRF, which instead of just casting rays at a single pixel, we actually cast rays in a cone that encompasses that pixel that allows for a much more physical representation of light flow as viewed by a camera. So this, just going to the MIP NeRF was a significant achievement and improvement. We also normalized our signals, so we standardized them so we're able to use our models a little bit better. We also incorporated a slightly different loss function, supervised loss function for our, when training. We add terms that basically focus on magnitude, spectral shape, and then looking at very specific bins where we know we are going to have some specific, going to have some hard time representing weak signals. So with that improvement, we can take a look at maybe global error statistics. On the top, I have just root mean square error as a function of the amount of training imagery going up. So basically 10% all the way up to near 100% of our imagery for training. And so this is asking how much magnitude we're matching at the pixel level, but averaged. Here, the spectral angle mapper is asking how much those spectral channels are changing. These should both go down as we increase the amount of data. And we see that for these two, for these error metrics, somewhere around the 50% mark, they kind of flatten out except for this little bump. Similarly, we're asking magnitude and shape, but from more qualitative, they're quantitative, but more image quality type metrics. So PSNR, peak signal noise, and spectral similarity index. These should go up with image quality, and that's what we see as we increase the amount of training imagery. So this is good, but this is just kind of a global averaging of what we're looking at. Here's some of that imagery with our nice animations. At the lowest end of the amount of images we used for training, here you see this rather poor rendering of our smokestack with the plume. The plume is absent. Again, we kind of expected that from our previous approach. But what's nice is already by 50 images, so basically like a quarter of the amount of training data, remember we have like 230 images, around a quarter, we're actually getting a pretty nice representation of the plume. And then by 100, that scene is pretty fairly well represented for our purposes. So this is just the image reconstruction. How does it fare for doing our task of detection, the detection task? Thank you. Again, for the 25 images, we don't really expect too much. So that's, there's no detection going on here. It's not picking out any signal. But what's really nice is that despite the slight differences in the image quality that I just showed in those renderings between 50 and 100 for these two NeRFs, it actually turns out that the detection capabilities are rather similar. So that means that for this task, you don't need the best representation in imagery. You just need to make sure you're picking up that signal, and then you can make this detection. So they're actually very similar in detection capability. But I've described some kind of global metrics, and then of course our looking at the qualitative or little animations of what those renderings look like and that detection look like. But you have to be very careful. Those metrics, especially those average metrics, don't tell the whole story. When we look at the pixel level, and in this case, the pixel level uncertainty, we see some potential issues with using this type of data. Here, I'm showing the NeRF output using 80% of our training data. But what I'm showing here is the variance, the estimated uncertainty at the pixel level, at each pixel. And what you see is, yeah, very good rendering, it seems, of our scene. And hey, there's a lot of uncertainty associated with the plume-specific pixels. At 80%, we know we're representing the plume well. We've seen that qualitatively and with the global metrics. But here, estimating the uncertainty of those individual pixels, it turns out that the model is not very confident about its ability to represent that. But that's just based on these estimates. What's really concerning is that if you only use 20% of the data, again, we know that we didn't see the plume with that limited amount of data. The concern is you don't see the plume at all, and it is very confident that it knows what is being represented in these pixels. So that tells us that when you don't have enough data, you really can't, even if you don't see a signal, this uncertainty that's being spit out is not representative of the fact that we know that something is there and it doesn't. So that is a major concern. So not full trust in these models yet. We're still working on this quite actively. But this brings me to the end of my talk here. Basically, I hope I've shown you like a story, a real data story of how machine learning can be used in a context where there might be reluctance or hesitancy to incorporating new tools, but it can be useful. And importantly, you need to encode the trust in using those tools for users who are going to be implementing them in the wild. For the target identification task, we showed that it is possible to use the information that's at the sensor, so that at sensor radiance, to make classifications, and very good ones, on materials. And we can encode a certain amount of trust, both by feature attribution methods, but also by building a neural network that allows us to understand more context about the decisions that it's making. From the target detection world, it turns out that incorporating multiple perspectives does seem to work or has applicability, but with the caveat that you need to have enough imagery, and quantifying what enough means here is a matter of further study. It's something that we have to think about more. And furthermore, the metrics that you get spit out, whether they're global or pixel level, are very important for interpreting for the type of task you're gonna be applying this to. But at the same time, this allows for a number of opportunities, both for ourselves at LANL, but perhaps for any of y'all who are working in this type of field. Further explainability studies for building trusted models is always good in order to get machine learning tools into the hands of people who need to adopt them. You need to overcome their skepticism, especially for the community that I work with in the remote sensing folks. For the NeRF models, we need to, of course, drive down the number of training images. It's unrealistic that you're going to get hundreds of images in the wild, especially when you're looking at a weak signal that you really want to characterize well. So driving down the number of training images and doing that explicit separation of target and background is important. And then for further study, going on and asking, hey, can we also incorporate other modalities that might provide other contextual information, such as synthetic aperture radar or something, or RGB cameras, and just slapping them on and seeing if we get more information from our NeRF models. And then finally, not related to the work, but just a few takeaways that I have either been given or wish I had been given as a student. There are a number of things that I put up here, but I've already mentioned. For example, I mentioned at the beginning, as a grad student, I made my work useful for others. This is something that only kind of I realized as I was getting close to graduating, but the code that I wrote could be used for others. In fact, the reason that I decided to open source my code was because I was using someone else's code that was really bulky and hard to use. But then when I realized, hey, I'm just going to rewrite this for myself, I made it useful and published it. And that was an extra paper that I wasn't anticipating when I started my PhD. So that was really nice to do. And it fits the goals of science. Someone should be able to repeat your work ostensibly, right? So empowering others to do that is, I think, really important. It also allows others to see like, hey, you've done this good work, and you can, put that on your resume, et cetera. And then something that's, I think has been important in my approach to my career is making sure you align how and what you do, aligning that with your work values and your personal values is really important. So for me personally, I hate driving and I don't like taking public transport. As long as I can bike or walk to work, that's something that I have been able to keep ever since my days at Rice. I think it's because I rode the bus in elementary school for like 45 minutes every day, one way, and that had an impact on me. So simple things like that can have an impact on how you do your work and what you do, and how you feel about it. And importantly, as you move forward in your careers, don't be afraid, especially early on now while you can, to take risks and step outside your comfort zone. And then from the personal perspectives, I think it's easier to identify the mentors you don't want to work with, but if you can find the ones you can work with very early, that's very important. They will be there for you when you most need it, and you'll be thankful for that. Again, aligning those core values is really important, and I think the way you actually do that is just listening to your inner voice because it will guide you. So that brings me to the end, and I'm in the land of AC, so I used to feel like this when I was inside living in Houston, but this is New Mexico in the winter, and I hope you all visit. It is very hot in the summer and all the snow's gone, so don't be scared by that, but would love to collaborate and hope you all enjoyed the talk. So thank you.
About 2 minutes for questions. Any questions for Dr. Hampel-Arias?
Yes.
May not be a point in your work yet that you're thinking about how you actually use these models in like in inference, but have any thoughts on like what compute requirements can be, and if that's something that you would like actually process on this line?
Oh, I see. Yeah, there have been efforts to put like GPUs on the planes, but just to answer your question briefly, what typically happens is the plane flies, collects data, and then there's a lot of processing on that data, because what the data actually looks like is just counts in specific wavelength bins, and then they have to get converted to energy, et cetera, and that's the data products that I use. But that data gets offloaded off the plane, and then we analyze it later. Doing on-prem or on plane processing is not super important for these applications. It's more about characterizing after the fact. But to answer your question about how much compute, the NeRF model typically trains in for single channel in like 20, 30 minutes. The big cube one takes overnight, like 8 hours. So at this stage, there's no anticipation of getting that training on a plane. But maybe if we have a pre-trained model of something of interest, that might be able to sit there and provide information. But yeah, it's not the best answer, but I hope that answers your question. It's not necessary. Yeah, and there was a question here. Yes. Yeah, in that case, yeah, I didn't detail that. In that case, it was an ensemble of models providing an estimate of inference variance. So many models give me the variance of the inference at that pixel. Yes. Sort of. That's kind of what I alluded to with the improvements that we made by changing, by changing the architecture from the vanilla NeRF, which just does simple INR, the implicit neural representations, then to a more sophisticated approach, which actually breaks up the model into several sub-modules and does this conical representation. And then, of course, we changed the explicit loss function from the NeRF modeling. And then it was actually suggested to me yesterday by someone who's more knowledgeable about Gaussian splatting, the newer model, the state-of-the-art 3D scene understanding modeling technique that combining NeRF and Gaussian splatting in very specific ways can lead to significant performance boosts and inference boosts, which I was not aware of. I don't know if there are any papers that actually